1 2 mic check. 1 2 1 2. Excuse. One, two. One, two, 1 2 3 4 5 6 7. Mic check 1 2 1 2. Mic check 1 2 1 2. Mic check 1 2 1 2. 4 5 6 7 8 9 10. I'm not so sure unless you ask him.
want to start by quickly going over the test we wrote on Friday to show you one possible way to solve it. Let me just open, oh no, I actually won't have to. So if I run Cabal test right now, then I get 9 failures because nothing is implemented. And hopefully in the end it should be 0. I make it bigger, hang on. So why doesn't my sidebar disappear? Second. Normally my sidebar automatically disappears when I click in the editor, but maybe that's an extension that the container doesn't have, probably.
The sidebar?
Yes, this. But it's fine. Or I can do it outside the container, maybe better.
Yeah, the solutions are the same.
Yes. So we do that again and not open it in the container this time. Well, so much for that. I don't know what I did, but I mean, I think it doesn't matter too much. Let me open it in the container. Sorry. Okay, whatever. Okay, so the first test was compute the list of integers consisting of all positive multiples of 13 which are less than 10,000. It is up to you whether you use map and take while from the prelude, list comprehension, or another technique. So I think we haven't talked about list comprehension yet, and also not about take while. But so let's first try to solve it with things we already know. So I can start with a list of ints. And if we knew take while, I could make this infinite. But now, I mean, for example, because we want everything less than 10,000, it's clear that if I, for example, take the first 10,000 ints, it will be more than enough. So this is now the ints from 1 to 10,000. Now we want the multiples of 13, sorry. So I can just map the function times 13 over it, for example. So now I have the first 10,000 multiples of 13, but I only want those that are less than or equal, less than 10,000. So, I mean, it's a typical application for filter. And I could do it like this. And now hopefully if I run the tests, I mean, now I get 7 failures, and the first one hopefully is somewhere else. Right. Oh, sorry, I was expecting to get an error here. That's because I already did that earlier. Let me just fix this. So now I still don't get that. I must try one more time. Yeah, now I get 8 again. 8 failures. Right, so okay, fine. So that was the first one. And of course there are alternatives. So alternatively I could have use function composition like this. And if we, if you use this take while that we haven't talked about in the lecture, but of course you can. I'm not in the REPL right now. So take while. Let me open a REPL quickly. So take while takes a predicate and a list and produces another list, and from the name it's clear what it does, so it applies the given predicate to every element in the list and then keeps them until the predicate becomes false, and then it stops. So if we wanted to use that, it would have a bit nicer, because then I wouldn't have to guess here how far I want to go. Then I could just take the infinite list, starting at 1, and instead of filter use take while. And let me just, instead of running the tests, do this length. Yeah, so it still seems to be correct. And please interrupt me if you have any questions.
And you can also use 1326.
Yeah, right. So this is this. Instead, instead of doing this map times 13 step, I showed you how you can use these dot dots, and also with a custom increment. So I could have done 1. So the next one would be 13. No, sorry, not 1. First one is 13. Next one is 26, like this. That should also work.
And if you know the length of the list, you can put a 10,000 at the end.
That's right. I could, it would have been even short. No, I don't even need to know the length of the list. I could just have done this, and that would also solve it. Okay, so that's maybe the shortest solution. Okay, what next? There's this, intertwine. So we have 2 lists of something and want to first take from the first list and from the second list and alternate between the 2 until one of them runs out of elements. And as we see from, here are all these examples, and as we see from this one, if the first list is empty, we immediately stop. So we don't, that's how it's defined from the examples. So we can write that down. So if the first list is empty, no matter what the second list is, it's empty. And if the first one is not empty, as we see from, do we see it from here, for example, or we take the first element, that x. So we start with this. And I think now the simplest way to write the rest is to simply recursively call intertwine on the arguments reversed. So if the first list is empty, it results the empty list. If not, I take the first element and then I recursively intertwine with the 2 reversed. And we can try this out on, for example, this ABCD XY, and that's what we were expecting. So I think that also works. I can quit here and run the tests again. Now, it's hard to see when this is so small. Okay, now we have 7 failures. So the first 2 seem to work. Now let's look at the next one. So there we are supposed to define this employee type in record syntax. Sorry, first name, last name, salary, and info of polymorphic type A. So let's do this. I mean, I showed you how to use record syntax in the lecture. So first name, type string, comma, what was it called, last name of type string, salary, type double, and info type A. So that's that. And with this, write a function that computes the full name of an employee, first name and last name separated by a space. So let's do this. And as we learned in the lecture, if you use record syntax, you have this these accessor functions that are called, are just the field names. So with first name E, I get access to the first name, and okay, fine. And we had this plus plus to concatenate strings, so I concatenate it with the space and then concatenate it with last name E. So that should do this. So let's see. Okay, 6 failures left, looking good. Write a function that doubles the salary of an employee and doesn't change any of the other 3 fields. Use record update syntax. So record update syntax we also saw. So the syntax is you use an existing record, and then in the curly brackets you just redefine the fields that you want to change. Everything else stays the same. So we only want to change salary, and that's supposed to be twice the original salary. So 2 times salary E. Let's try it. Still 6 failures. Did I do something wrong? No, I don't know why it's still 6.
And can you scroll to the top?
In the test?
See the first?
Yeah. Sorry, let me just clear this and run it again. Okay, I made a mistake, obviously. I forgot one part. There was I forgot here it said derive show equal and read instances for this type. I forgot that. Okay, 5. Looking good. What next? Make employee an instance of class functor. So that's very easy with record update syntax. So, the other fields, of course, stay the same. So we have this info field. So maybe I should add this, as I told you, instance 16 that I can give a signature for this. That makes it easier normally. Okay. So fmap takes a function from A to B and turns an employee A into an employee B. So one where the info is of type A into one where the info is of type B. And so we have a function and an employee, and using record syntax again, so there's nothing we can do about the other fields, so the only interesting one is info. And here we now need something of type B, and we don't know anything about the types A or B, so the only possible way we can produce a B is using the function f. But in order to use the function f, we must supply a value of type A, and the only value of type A we have available is the old employee field. So the only thing we can possibly do is this. And that doesn't compile. Oh, because okay. So let's see. 4, getting there. Write a function that forgets the info of an employee but keeps the other 3 fields untouched. Use fmap. So we just need a function from A to unit, and because unit only has one value, namely unit, there's only one function, namely this one. And we can of course simplify that with const. And why? Okay, fine. There is something built in that does that, but you don't know that yet. So that just keeps everything as is and then applies, I mean, as we saw in the definition of fmap, it just applies the given function to the info field. So this does exactly what we want. It replaces the info of type A with unit. So this should bring it down to 3. Yep. Now write a function that takes a list of employees and extracts the info. The resulting list should contain the info of each employee in the argument list in the same order. This of course is a very simple application of the map function, and we are done. Now only 2 left. Okay, now we have a new tree type, so-called rose trees. I don't know why it's called a rose tree, whether there's a mathematician or computer scientist called Rose, or whether it looks like a rose. Probably it's a person. So, I mean, the trees we had as examples until now were these binary trees with data in the leaves and nothing in the nodes. And the rose tree has data in the nodes, and it can have arbitrarily many children, so it's not just a binary tree. And it has this very compact definition, just one constructor, because the base case is basically when this list is empty. So that's the leaves, where it's fork a empty thing. Okay, the first task was collect all data from a rose tree in a list. So let's do this. Okay, we only have one constructor, fork. And because it said pre-order, so the first data in this rose tree is the X. And now we somehow need to get all the data in the X's, which is a list of rose trees. And I mean, there is a function called concat map, which would be perfect here, but we haven't seen that yet. So let's do it by hand, maybe by defining a helper function that I call go. So go takes a list of rose trees and produces all the data in it. And standard pattern on lists, so we have 2 cases. If it's the empty list, then there is no data in it. And if it's a tree and some more trees, then we can first get the data in the first tree, which is the function we are just defining, and then recursively apply go to the tail of the list. So that should do that. Okay, looking good. And if you, I mean, there is a function, I mean, we saw this concat, or maybe we didn't, but that's just another name for this plus plus. So to concatenate 2 lists, sorry, forget that. We haven't seen concat yet. So there is a concat, which, I mean, the plus plus takes 2 lists and combines them to 1 list. Concat takes a list of lists and flattens them to 1 list. So we can demonstrate, for example, if I have a list of strings, and then concatenates all of them to 1 list. And then we also have, with this we could already solve that, but there's also concat map, which takes a function from A's to list of B's and then a list of A's and turns it into a list of B's maybe you know that from other programming languages. I think it's called flat map often in Scala, for example. So, for example, if I take, I don't know, concat map a character to, sorry, let me just import data.character. If I take concat map, mapping a character to, for example, itself and to upper C, and have a list A. So if I only did map, then I would get a list of strings now where this function is applied. And concat map is just basically the combination of concat and map. So it first maps and then it concatenates the results. And we could have used that here. I mean, if you had known that, then instead of defining this go, we could just have set concat map rows to list access. And I could have done it like this as well. But I mean, you didn't know this concat map. But that would probably be the...
And they already knew polar and concat, so they could have defined concat map and it says like polar of the composition of concat and rows to list, then you will get the same result without knowing the existence of concat map.
Right, whatever. But all of this is fine. And what was the last one? Okay, sum all data in a rows tree, use sum for lists and rows to list. I mean, this, of course, after the previous work is super simple. I mean, we just convert it into a list and sum it. And, sorry. And that's it. So now everything passed. So that would have been one possible solution for the test. Any questions? Otherwise, we can proceed with the lecture. Okay. Then let me close this. Right. Okay, so today we want to talk about testing in Haskell. Testing, of course, always an important topic for programmers. And we want to talk about why you need testing in Haskell. Then we will look at one famous Haskell testing library that has inspired testing frameworks in many other languages. Then we look at the case study. And this generators won't make sense now, so we have to wait until we get there. And finally, how you can do program coverage in Haskell. So first, I mean, what is testing? Probably you all know anyway. I mean, you want to somehow convince yourself and maybe your managers or your customers that your program is correct, and show that, I mean, the common cases work correctly, but also the corner cases work correctly. And in principle, testing can't prove that there are no bugs. It can just increase your confidence that there are no bugs. Except if there are only like finitely many possible cases, and then of course you can try all of them. If all of them give the right result, then you have proven that there are no bugs, but that's very uncommon in practice, of course. And I mean, what does it mean that a program is correct? would mean that it follows the specification. So what's the specification? How do you specify a program? And of course there are many different approaches. I mean, normally it's done like verbally in prose in English. And somehow you must establish a connection between the specification and the implementation. Of course, if you use some formal language for specification, basically what we are doing now is to use Haskell itself to specify Haskell programs. Then you can use automatic tools to prove or at least increase your confidence that your programs are correct. And of course, I mean, we will see examples of that. It's also possible that there are bugs in your specification. So if a test fails, it doesn't necessarily mean there's a bug in your program. There could also be a bug in your test. But this is all applies to every language. There's nothing specific to Haskell. And I mean, in Haskell, I mean, people often, or Haskellers like to say, if it compiles, it's correct, which is true to an extent, I think. So there are much fewer bugs in Haskell than in, like, if you write Python, because the compiler does catch so many problems already. Like typical, or whatever, in other languages you have these null pointer exception problem that you pass null where you don't expect it. Or in Python often you have, or JavaScript you have this problem that you first have to check that all the arguments have the right type, because it's an untyped language, dynamically typed. So these classes of errors, they all fall away in Haskell, but nevertheless there are still some that the type system can't express. Although this is, I mean there are also languages that are like similar to Haskell but have an even more powerful type system, and there is something called dependent types. And with dependent types, in principle at least, it would be possible to completely specify your program in the type. So if it then indeed if it compiles, it's correct. But even if that's possible, I mean, in Haskell, I mean, we probably won't have time for that in this class. But in Haskell is very far on the way to dependent types. So especially with modern extensions, you can do almost anything that you do with dependent types in Haskell as well. So probably you could almost every Haskell program type it in a way that if it compiles, it's correct. But that would be very, very, I mean, a lot of work and overhead. So most people don't go that far and try to find a balance. So you use the compiler and the type system to find the most common bugs, but you accept that there's still some leeway for bugs to sneak in at runtime. And then that's where testing comes in, so you must find those bugs at runtime. So it's a balance, and with more experience you will hopefully get a feeling for which invariants or properties of your program you should try to express in the types and which you should just use testing for. But as the last point that says, because we have types, we can at least test interesting properties. So we don't have to test that something is not null or has the right type or things like that. And there are lots of tools. I mean, if you look on Hackage in the category testing, there are lots of testing frameworks for Haskell, like HUnit, QuickCheck, Hedgehog, SmallCheck, and whatever. But so we obviously can't look at all of them. So we will concentrate on QuickCheck because that's one of the most famous ones, and it's also one of the oldest ones. And it uses this approach which actually is only possible in Haskell, at least in its purest form. And it's interesting. And this is type-driven testing with random test case generation. So instead of writing just unit tests, one test case at a time, you basically specify properties your program should have, and then the framework automatically generates random test cases, as many as you want, and tests whether the properties you specify hold. And so everything, I mean, the tests are themselves Haskell programs. I mean, of course, that's not only true for Haskell. In a lot of languages, the testing frameworks are written in the same language. So, I mean, this is already helps you that your tests are correct. And so the history is that it was developed in the year 2000 by Kuhn Klaassen and John Hughes. And actually, John Hughes has worked quite closely with IOG on Plutus, for example, on to extend this to Plutus or to smart contract testing. But I mean, in 2000 he did that for Haskell, and the idea was so powerful that it has been copied to, by now, probably all languages or all common languages. So, of course, functional languages like Lisp or Scheme or Erlang, but also things like Ruby and Python and Java and, I mean, basically everything. So, I mean, but in Haskell, that is one of the examples where, even though Haskell is not a mainstream language, it inspired, I mean, this idea was so powerful that it leaked into basically every other language. And I mean, John Hughes, these days, I mean, he was one of the original people on the committee that designed Haskell, but these days he mostly does Erlang because, and he ported QuickCheck to Erlang because I think Sony Ericsson uses Erlang, and they have, I mean, they have insanely high quality requirements for their networks, and they had problems, and then QuickCheck could help them fix their bugs or find their bugs. Right. So yeah, that's a beautiful idea, and it's much more powerful than simple unit tests. There's also, I'm not sure whether we have a link for that, but there's a, if you know Computer File, the YouTube series, there is one episode with John Hughes where he uses Erlang, I think, not Haskell, to debug something, and it's very interesting.
Yeah.
So maybe we can look up the link and put it.
15 minutes.
Yes. Okay, so let's look at an example, and let me first copy this. So this is a sorting function, not a very efficient one. It's insertion sort, so it's O of n squared. So I mean, there are better sorts, of course, a quick check, but it's just an example. And there are like at least 2 bugs in this program, but that's the point. I mean, we're talking about testing today. So let me just try to copy this. I think I was confused earlier. I mean, the sidebar always is there. Just the Explorer has to go away. So all good. Okay, so we have the sort. Let me just peek. Okay, it's specialized for ints. I mean, we already saw that in data.list, the sort provided in the base library is, of course, not specialized just for ints. It's for all ordered types, all instances of odd. But just to keep it simple. So sorting the empty list is the empty list, and sorting a non-empty list uses this helper function insert, and insert takes an int and a list of ints, and the idea is it inserts the given int at the right position in the list. Let me just check what it was called. Okay, if the list is empty, then I mean, we just put it in, the x, and if not, we check whether x is less than or equal y, and in this case, we prepend it to the list, and otherwise, the first element will be y, and we recursively insert x into the tail. And what, oh sorry, y here. Okay. So I mean, it's horribly wrong, but the idea is you start, I mean, you recursively sort you sort a list recursively by basically inserting elements at the right spot. And this is done by the insert function. The idea of the insert function is, I mean, you check whether the new element you want to insert is the smallest one, then you put it at the head. And if it's not the smallest one, you recursively insert it into the tail. So that's the idea of insertion sort. I mean, yes. So, right. And now we somehow want to, and of course it type checks. I mean, the compiler is happy because the compiler, I mean, just sees lists of ints. So of course it can't check that it actually sorts. Okay, and there are obviously bugs in there. And now how would we specify sorting? And of course, ideally a specification would be as precise as necessary and no more precise than necessary. So we want to, I mean, the second thing is that we don't over specify it so that the implementer still has the freedom to choose a good implementation. And on the other hand, of course, it must be precise enough, because otherwise the implementer basically has too much freedom and can do something that was not required. So, I mean, ideally we would find a specification that distinguishes sorting, like a correct implementation of a sort function, from all other operations. But that doesn't force us to use a particular sorting algorithm. So the specification should work for everything that sorts, like the built-in sort or whatever, a merge sort or quick sort. But it shouldn't work for a function that doesn't sort. And we can just start with a property that's obviously necessary but not sufficient. Namely, sorting a list shouldn't change its length. If I sort a list of 7 elements, afterwards it still has 7 elements. And we can just write this down as a property. And I think I could, of course, do this in the same module, but actually this time I set up when I use Cabal init, in the end it always asks, should I create a testing function, testing suite for your module? And this time I said yes. So it created this. And it's very similar, this stanza is very similar to executable, what I showed you last week. So these things are basically all the same. The only difference is, first of all, it's called test suite instead of executable. And secondly, there's this type thing. And basically what this does is, we can look at this. So it looks very much like a main program. So it's also module main. It has a main function of this type IO unit. And the idea of this is, this type is basically what the test runner will do. It will execute the main function. And if that exits normally without an error, then the tests count as passed. And if it doesn't, then the test fails. So it's basically just a very thin wrapper over executables. But then you can use Cabal test to actually run your tests. And at the moment, it will, sorry, I think I'm, just a second. Am I? Yeah, I must be in this. I wasn't in the right folder. Just a second. Now why does my, okay. So now I can do Cabal test. And now it will say it passed. And that is because at the moment the main program just is this. So it doesn't create an error. So it doesn't test anything. Okay, let's, for the time being, keep it like this, but I just work in this here. And so now in the slide, sort preserves length. So I just write a predicate on lists. That was a mistake, sorry. So in the property for a given list XS, it's just I sorted, and for this I must import my, and this is called testing. So if I apply a sort to my list and look at the length, then that should be the same as the length of the original list. So this is just another Haskell function, and if sorting, the sort had this property that it doesn't, the sort function doesn't change the list of the length I'm sorting, then no matter which list of ints I'm applying to it, or to which list of ints I'm applying it, I should always get true. And if I find a list where this results in false, then I found a list that violates this property. So where sort does change the length of the list. And now let me open the REPL. And now, because I have now two things, I have the library and the test suite. When I open the REPL, I must tell it what I want, and this test suite is called testing test. So I'm there now. And let me import QuickCheck. That's this QuickCheck library, and it's called test.QuickCheck. So, and there's a function QuickCheck, and that takes some prop which is testable and returns IO. So it will turn out that this sort preserves length that we just defined is an instance of testable. So we can do QuickCheck sort preserves length. And now let me make it bigger. And it immediately returns and says failed, falsified after 4 tests and 2 strings, 0, 0. So that means, I mean, we will look into how it works a bit later today. But I mean, roughly what it does is it generates random lists of type int and checks whether this property holds. And I think by default it tries 1000 or so. And if it finds one where this is violated, then it reports it. So we can read this now as the list 0.0, I mean 0,0 doesn't have this property. So we can check it. So I mean we can call sort on this list, and the result is indeed a list that's not as long as the original list. So QuickCheck found a bug in the program and gave us a counterexample. And if you wonder what this shrink means, so the way QuickCheck works, it generates, I mean, these random lists in this case, and they are more and more, so it starts with very simple lists, like the empty list or a list with 1 or 2 elements with small numbers in it, and it tries more and more complex lists, longer lists, larger numbers, and so on. But when it finds a counterexample, it doesn't immediately report the counterexample, it tries to simplify it. So there is a concept of shrinking in QuickCheck that knows how to make like things, Haskell values simpler, and it will try that until it can't simplify it anymore. So that means that we will often get the same counterexample even though the lists it tries. So in this case, I always get this counterexample, even though the lists QuickCheck randomly generates are completely different each time. But this shrinking makes it, first of all, more predictable and more deterministic, and also simpler, because, I mean, now you have a very simple list where you can try to find out why this error happens. Whereas if you got now a list back with huge numbers in it and 100 elements, it's much more difficult to understand why for this list it goes wrong. So QuickCheck tries to not only give you a counterexample, but a minimal counterexample, which is as simple as possible. So basically, this means that for lists of length 0 and 1, it will work. I mean, the property holds, but no longer for, so the simplest counterexample has length 2. And now we can understand to fix the bug, or I mean, find the bug. Right. And so let's look at the implementation. And maybe you have spotted that already here in insert. So in this case, I have my X, and the list I want to insert into is not empty. And in the case that X is less than or equal Y, here I put the X first, which is correct, but then I just say Y is. So the Y is dropped. So I basically drop the Y. Therefore, in this case, the list gets shorter. So I can fix that by leaving it there and try to fix it. Okay, now we can, I think I must restart the REPL for this. Sorry. Oh yeah, and actually I can also, just 1 second. I mean, if I wanted to turn this into a proper test suite, I could import test.quickcheck here. And then here, for example, I could do and quick check sort preserve select. So now this would, and in this case, because it's only one thing, I wouldn't need the do. So now I could do this cabal test. Right. And it's passed now. So let me just fix the, just reintroduce the bug once again. Just want to show you what happens if it, why does it still pass? Sorry, something wrong obviously. This is a bit silly. Just look at this. So it does find the bug, and then for some reason it still passes. So maybe quick check is not the right command. Let me just.
If you run command test,
Yeah, it didn't work. I mean, it does find the error, but it doesn't report it. I think that's the wrong way to do it. I think actually that was a bad idea to generate this test suite. One needs some sort of H unit quick check or so.
a framework.
A framework.
Maybe that would be easier, but you can do
I could do this now, but I think it's a bit. So the problem is this quick check is not the right thing if you actually want a test suite. I should have tried that earlier. This is more for interactive, but there are ways to turn it into a proper test suite. Maybe I can explain that later. So for now, we should just forget about the test suite, and let me just change this. Let me just put quick check also in. So sorry about that. Just a second. So let me just change this that I have. So I remove this here. And I just import quick check or make quick check available in my thing. And let me just get rid of all of that. Okay. I should have stuck with how it was. I'll show you later tomorrow how to turn it into a proper test suite. So for now we just use the REPL. Okay, and so I remove. Oh, now I have to rewrite this preserve length thing. I should have copied that first. But no matters. So sort preserves length from list of into pool. Preserves length XS, length sort XS, length XS. Okay, and I should import quick check here now. Okay, let's do it again. So if I do quick check sort preserves length. Okay, I find the bug, and if I fix it and reload. Okay, so now it says okay, pass 100 tests. Earlier I said 1,000, so by default it's only 100, but that can be configured. So now that seems to be correct. So now our sort preserves length. Okay, and are we done now? I mean, is it now correct? Yes?
When it comes to importing, in the previous class, I was trying to import the test quick. Would we just go back to
The editor?
where you have imported yes, as you can see there, import test quick check. It's like it's not defined, right?
No, it's defined, it's just not used because I haven't used quick check anywhere. I mean, I have to in the Cabal file referenced as a dependency, quick check as a dependency. It's on Hackage, it's called quick check.
That warning is because he's not using it in the file, but he's using it in the record. But the compiler doesn't know.
So does it bring any kind of impact to the file?
Ah, okay. No. Because when you compile, the compiler checks like what you're actually using and only adds that to the final compile code. So if you import a whole library which is used 3 of the functions, the compiler only takes those 3 functions into account. So
Yes.
by now, if Lars tries to compile it, it
Won't
like
do-
the actual binary won't have anything of quick check.
But I would get this warning probably somewhere that quick check is specified as a dependency but not used. Or no, I don't get that because I do import it. But yeah, it would. So I think it's fine. But of course, normally in production code, I would try to get rid of all warnings. Okay, are there any other questions at this point? Okay, so we have found one bug, but obviously that doesn't mean that the sorting function is correct. It just means that sort doesn't change the length of the list anymore, probably. I mean, we haven't proven that, but at least we have tried it for 100 random lists and can be reasonably sure that this part is now correct. But I mean, for example, I could, if I replace sort by the identity function, that doesn't do anything, that just returns the original list. And do this again, then it also passes, right? Because the identity function also doesn't change the length of a list. So that is an example. We said the specification needs to be precise enough, but only as precise as necessary. So obviously this is not precise enough. Just to know that the length is not changed doesn't mean that it actually sorts. Okay? So this is too weak. The test is too weak. Right, so I showed you that, but first this abstraction. So, I mean, of course, as always, I mean, when we talked about I/O on Friday, we said that, of course, what you learned about functional programming before is still true. The same is true for testing. So, I mean, here, for example, is a useful pattern that, sorry, let me just check on the slides. Right. So we can abstract it. I mean, now we said the length should be the same, but we could have other properties that should be preserved. So we can call this preserves. So preserves P, and basically abstract away this length thing and say P of sort XS equals P XS. Sorry. Okay. So we could generalize this. So now we just use it for length. So the idea is that length is an invariant of sorting. I mean, it doesn't matter. The length doesn't change when I sort. And we could capture this idea into a higher order function, more abstract function, preserves, where instead of, sorry, there's something wrong. F. Sorry, it's not. Okay, now the type is wrong. Right. Yeah, sorry about this. So, right. And I mean, maybe I should, I don't know. I mean, I don't know, I could leave it like this. And let's leave it like this. So in this case, I mean, this is then we could rewrite it as
Just before you revise, what does F and P? Now last week we were assuming this thing like I was assuming them, but
sorry,
maybe
what?
just tell me what F presents and P
What do you mean?
in line 20.
Yes,
F
yes,
preserves P.
yes.
Yeah, what does that mean?
Means I'm defining the function preserves, which has 3 parameters, fp and xs, with this one equation.
Maybe if you put preserve
Yeah, I mean that's,
as a prefix, it will be easier to.
yes, I mean I could equivalently, sorry, editor problems. Yes, I mean equivalently, as we have learned in the very first lecture, that's exactly the same as this. I mean, I'm just because infix notation reads nicer. So I mean, if I do this, then I could, sorry, I could use this now and say gly sort. And that's the point. I mean, one can extract a useful like abstraction from that. In this case, of course, it's stupid because I only use it once. But if I now find something else that should also be preserved by length, then maybe it's useful. Okay. But that has nothing to do with testing. That's just Haskell. That whenever there's like a useful pattern or something, one tries to abstract it. And okay, and I already showed you the example that the identity also preserves length. So that isn't very helpful. So I mean, we could say and if we quick check that, and it also passes. So this property that it preserves length doesn't distinguish between sort and an identity function, the identity function. But the identity function obviously doesn't sort, so this is too weak. I mean, this doesn't show that our sort is correct. Okay, so we must somehow come up with more properties to test. Right. So I mean, the obvious thing to test would be that after sorting, the list is actually sorted. So let's define a function sorted.
Maybe is sorted, so it's.
Yes, I mean on the slide it's different, but it's fine. So the empty list is sorted. A list with just one element is sorted. Right, and a list with at least 2 elements is sorted if the first one is less than the second one, and recursively the tail of the list is sorted. And yes, there's a bug, but that's the point. So we keep that now. So okay, I mean, first we said sorting should preserve the length of the list we are sorting. And that does that, our implementation does that. But then we came to the conclusion that that's not strong enough because something simple like the identity function also preserves the length. So the obvious thing to test for a sort function is whether it actually sorts. So it might be a good idea to implement such a predicate that checks a list whether it's sorted or not. And I mean, I can sort it 1, 2, 3, 4, 5. It's true, and so that looks good. Right. And now what can I do? I mean, what property do I want? I can call that, I mean, sort ensures sorted. So I want to test that after I sort my list, it's sorted. So let's do this. Sort ensures sorted. So I sort it, and then after I've sorted it, it should be sorted. So this is obviously a nice property to have for a sort function. So let's quick check that. Sort should, after I reload. Sorry. And lo and behold, it finds a bug. And it says that, again, the list we had earlier, this list with 0, 0 is a counterexample. So let's see what sort of 0, 0 does. And that looks perfectly reasonable to me, right? So something is wrong. I mean, quick check says this property doesn't hold. And it says 0, 0 is a counterexample. But when we try it out and check what actually happens when we sort 0, 0, we do get a sorted list. And I mean, it's correct. 0, 0 sorted is 0, 0 again. So what can be the case? I mean, I mentioned that earlier at the beginning. I mean, obviously, there can also be bugs in our test. So the problem is that this is sorted function that I wrote. If I apply that to 0, 0, it says false, even though it's true. And the bug is here because it checks whether x is less than y, but it should also accept if x is equal y. So now this is true. Now I can do quick check again. So the moral of the story here is, I mean, finding a failing test case doesn't necessarily mean there's a bug in your program. There could also be a bug in your specification. Okay, but now it finds another counterexample, which is now 3 elements long. So we are getting there. I mean, our bugs seem to be more and more subtle. And okay, let's see what sort of this actually does. Right, and that is indeed a counterexample. Because the -1 is the smallest element, so that should be sorted to the front. So quick check is correct. But it seems only to happen with lists of at least 3 elements. And now if we look at the implementation again, can somebody spot the remaining bug? Well, the line 7 is wrong because if I have a non-empty list, what I do here is I just insert x into the list. So I mean, x will be at the correct position, but I mean, xs is completely arbitrary. So I, of course, have to first recursively sort the tail of the list and then insert the head at the right position. So if I do this, okay, fine, but I don't. Okay, now that also holds. So now it's preserving length and it's returning sorted elements. So is that now I mean, I think it's correct now, actually, the sort function. But the specification, do you think it's sufficiently specified now? I'm actually not sure whether in the slides it goes on. Okay, so this is this bug in the implementation. Found it. Found it. Okay, so we are not right. So that's like a puzzle now for you, right? So we have a function from lists of ints to list of ints that doesn't change the length of the list, and the resulting list is sorted. Does that mean that the function is a good implementation of, or correct implementation of the sorting? Or can you think of some other function that does not sort but has the same properties? While you think about it, I can do what I did here with this preserves. I can do something I call ensures or ensures. So I can rewrite this sort ensures sorted as sort ensures sorted. Right. So the same idea to abstract that. So does anybody have an idea for a function that does not sort but has these two properties? It preserves the length and results in a sorted list.
What if it's negative? Less than equal takes into account negative numbers.
Mm-hmm. Right. Well, one way, for example, is to just try to, so on the slides it's called evil no sort. For that, there's a function we haven't seen yet, or maybe in the exercises, I'm not sure. That's called replicate. That takes an int and an a and produces a list of a's, and it just replicates the given a, the given number of times. So, for example, replicate 10 character x is the string with 10 x's. So I can do an evil no sort by just replicating length xs times the number 42. So if I now do my evil no sort of whatever, 1, 3, 47, 0, it just gives me the same number of 42s as my original list was long. So it's sorted because it's just constant and it has the right length. So I can do quick check evil no sort preserves length. Preserves length. And I can also do evil no sort ensures is sorted. And that also passes. So it's still not good enough. Any idea what we could check to make sure that that this evil no sort no longer works? Yes? Some? That's true, that would work in this case, but I think I could still write an even more evil no sort that would also preserve the sum. I mean, but you're right. I mean, that's a good point, so I could check this. So if I have quick check, sort preserves sum, that's true, but evil no sort does not preserve the sum, because it finds a counterexample, the list 0 gets mapped to the list 42, so the sum is 0 and there it's 42. So yeah, it's very good. I mean, I could do that. But that still won't nail it down. I could still do something like take the list that as first element has the sum and then only zeros, or maybe the other way around, depending on whether the sum is greater or less than. So it gets more and more tricky to write something, but I think I could still break that property with the non-sorting thing. Yes, but that was good. I mean, it's a good point. I think, I don't even know what he has here. Right. Right. So I mean, what does sorting mean? You basically take the elements of the original list. That's the point. I mean, you don't add something like 42 or so. I mean, it must be the elements of the original list, and you like reorder them in sorted way. I mean, that's what sorting means. You can permute your elements, but you mustn't add a new element or remove one. So you must take the elements of the original list and permute them until you get a sorted order. And I think on the slides it uses permutations, and I think it's in exercises somewhere, or is it built in? So if we have import data.list, there's a function permutations that gives you all permutations of a given list. So let's try it with, for example, 4 elements A, B, C, D. So it gives you it takes a list, it returns a list of lists of all the possible permutations of the elements of that list. So if we use this, then we can say, can define a new helper function, f permutes and say, okay, if we apply the function fxs, then it should be an element of all the permutations of xs. Right. Okay, it automatically imported this permutation thing that I just did in the REPL. So, I mean, this type signature looked a bit scary, but so we have a function that takes lists to lists, and this property says when we apply the function to a list, then what we get is a permutation of the original list. Now we can try this. Quick check, sort permutes, sort permutes. Okay. What now? Oh, so because I imported, but I didn't, or here I did. I imported data.list, and that of course contains a sort function. So that was bad. Okay, quick check. Sort mutes. And now I'm not really sure what the point here was. I mean, now the problem is that these lists, I mean, permutations, as you probably know from school or university, I mean, it's factorial of the length of the list. So as soon as it tries longer lists, I mean, it's a very expensive test. Because, I mean, for, I don't know, what 10 factorial is, we can, let me interrupt this. For example, take the product, the first 10 It's already 3,628,800 permutations of a list of length 10. And I mean, we haven't looked at the details of QuickCheck yet, but I mean, it tries these 100 random lists and they become longer and longer over time. So it will probably in the end have lists that are much longer than 10 elements. And then it takes a crazy amount of time to compute all permutations. So that's why, even though now it's correct, I think, and fully specifies it, it doesn't work because it takes too long. So I don't know whether on the slides there's a solution for this. No, there's not. So I mean, one could, of course, I mean, the problem is that this is a very inefficient implementation of permutes, because you basically generate all possible permutations. I mean, obviously there's a faster way, like a quadratic way. I mean, you can start with the first element and check whether it's included in this second list, I mean, in the original list. And I mean, you just check that all the elements are included in the original list and remove the element maybe. I'm not sure whether I should do that.
No, I think it would take
too long maybe.
Yes.
Okay, but so the problem is, I mean, this is correct, but it's inefficient. Because as I said, if you have a list of length 10, then there will be more than 3 million, this year will be more than 3 million. And I mean, because of laziness, it's not a memory problem, it just tries one by one, but it's a time problem because it has to try up to 3 million lists until it finds the right permutation. But I claim it's much easier, I mean, you can do that faster, you don't have to generate all permutations first. So in principle, this is now correct and that would fully specify it. But yeah, maybe we don't need to write a more efficient version of permutes. Okay, are there any questions at this point? Otherwise, I would suggest we have a short break, and then after the break, we look how QuickCheck actually works and how it does that.
Are there some properties which automatically imply you don't want to do about
Good question. Are there some properties that imply others, so you don't have to check all of them?
Sure, I mean, for example, this one would imply the preserve length, because permutations all have the same length. So if I have this, I only need this one and this ensure sorted, that would be a full specification of sorting. Then I wouldn't need the length anymore, because a permutation always has the same length anyway. So if it's a permutation, it also has the same length. And of course, in reality, people very rarely fully specify their stuff. So I mean, that's an ideal that you have a full specification, but I doubt that that ever happens in practice. So you just try to get as close as possible. Because sometimes writing a specification is as much work as writing the whole thing. So often in QuickCheck there's this problem that you sort of replicate logic in your tests from your implementation. So I mean, it's also a trade-off. You just want to catch as many bugs as possible with not too much effort, of course. Are there other questions? Okay, then let's have a short break, 10 minutes or so, and then we look at QuickCheck.
100% coverage is equally bad as 0% coverage.
Yes?
Yes, okay. That's it. Now Lars is going to show something.
Yes, I just wanted to, Robertino pointed that out to me, and that's a good remark to make. If we go back to the test, this is now the version without the solutions. No, it's not for some reason. Never mind, I sorted that out. I somehow made a mistake and now I have the solution everywhere. But right. The point is that when we gave it to you, it compiled. Even, I mean, so it was something like this here, and I mean this was whatever error. What did I do now? It was something like this, and I mean it compiled. Right, it did compile because these things now. I mean it was with error instead of undefined, but nevertheless. So it was something like this. Yes. So I mean, when you got the test, it compiled. So Cabal build compiled. And of course the tests failed. Right. And it's always a good idea to keep your program compiling, because, and what is particularly bad is if you have a syntax error somewhere, because then I mean if you just have an error, I mean for example if I do this, I don't know, whatever, 42. I mean this is now a compiler error but not a syntax error. So if I do Cabal build, then I will get an error that it expects something of function type but gets a 42. But now, I mean, if I have another, whatever, silly, I mean, I will still get, it will still try to compile the rest of the program. So now I have two compiler errors, and it indicates both of them. So that's already, I mean, that's still okayish. Even though if you have lots of errors, then it gets like, it's easy to overlook like a new one. But it's even worse if I have a syntax error. So if instead of 42 here, I, for example, just write equals, then if I build, then it just tells me, yeah, pass error. And it doesn't, so then I don't see this one anymore. So that's particularly bad, because then, I mean, if once you have such an error, then the compiler doesn't help you at all anymore for other errors. So therefore, it's always a good idea to keep your program compiling. So if you get stuck with something, like now with this 42, no, with this equals, where was that?
One more.
This one. So if something, then you should like get the original back, ideally, or replace it with undefined or something, because we know undefined works everywhere. So now you get this, I mean, this is no longer an error for the compiler, and you see your other errors again. So it's never a good idea to have hundreds of errors, or it's even worse idea to have a syntax error, a parse error, because then the compiler doesn't tell you anything.
And you can still use the holes.
Yes, you can also use the holes. I mean, then you do get an error, but at least it's not a syntax error, a parse error. And then it tells you what is expected there at the point of the hole. Yes, so that's especially for something like tests or so. It's if you get stuck with one question but maybe want to work, I mean, continue with the next ones, then it's, I mean, it's bad if the compiler doesn't help you at all anymore beyond that point. So that was just that remark.
The compiler is a companion, it's a helper. If you lose it, you're alone, like almost writing in a text file.
Mm-hmm.
The best friend.
Yeah, it's your friend.
Okay, let's go back to quick check. And I already showed you that. I mean, in order to use it, you must import test.quickcheck. That's what it's called, the module. And it's in the package quickcheck. So in the Cabal file, you need to, wherever you want to use quickcheck, you need to, as one of the, I mean, I showed that already, but I can show again the Cabal file. So here now I have this quickcheck as a dependency. And at the top of my module, I have the import test quickcheck to make it available. And then you define properties like we did. And then you can call quickcheck to test the properties like we did. And I mean, we can show you tomorrow maybe how you can turn this. I mean, this is a manual process now, an interactive process. But there is a way, I mean, there are ways to turn it into a proper test suite so that you can make it part of continuous integration, for example. And that Cabal test then works on this. And as we see, this is an overloaded type, so quickcheck results in an I/O action, but of a polymorphic type prop. But prop must be of an instance of testable. And as we saw, when I execute quickcheck, then it prints the result on the screen, either that it passed all the tests or it gives you a counterexample. And so far, all our properties have been of this type. I mean, because our running example was a list of int to bool, and we had these three things: preserves length, ensures sorted, permutes, and they were all of this type int to bool. And in that case, what quickcheck does is generates random lists of ints and applies the functions to it and checks whether the result is indeed true. And for 100 cases by default, and if it's false, then it shows it shrinks and shows a counterexample. I mean, that we saw that in action. But it doesn't, of course, have to be of this type int to bool. It can, for example, we can take this example. Append length, let's see. Should I maybe implement all of those? Okay. So append length, A to bool. Given two lists, would check that the length of concatenating the two is the same as the sum of the length of the original lists, for example. Let me just see what else. Plus is commutative. Let's take two ints. And would check that x plus y equals y plus x. For example, what else? Take drop. An int and a list of ints. I think we haven't seen drop yet. So take, I showed you. So for example, take 3, A, B, C, D, E, F. Takes the first n elements of a list and drops the first n elements. So if I use drop, then I'm left with the rest. Maybe I should have, yeah. So here the property is that take n access plus drop n access equals access. And what else? Drop twice. I mean, yeah. Drop twice. 2 ints and the list of ints. So here the property would be drop precedence error, sorry. Right. Right, and these are all things I could test with quick check, so it's not limited to into bool. So for example, I can do quick check plus is commutative, and that passes. And I can do quick check tape drop, and that also passes. And I can try quick check drop twice. So here the idea is if I first drop n elements of a list and then m, that should be the same as if I drop m plus n elements. But lo and behold, it's not. And we see that now the output looks a little bit different. So earlier we got one counterexample, and that was because we had something of type list of into bool. So there was one parameter basically. But now quick check doesn't just generate random. I mean, what quick check does now is it generates a random m and a random n and a random list, and then checks this property. And if it finds a counterexample, it prints all three. So this is now -1, 1, and the list that just contains 0. And so we see that this property actually is false. So if we try the two sides, so if we drop -1 of dropping 1 of 0, that's okay. That's the empty list, but if we drop 0, the sum of 1 plus -1, it's that. So the problem is somehow with negative numbers, because then it doesn't do anything. So this property is actually false. And we get a counterexample. The properties are not important. This is more about that quick check can't just deal with functions with one parameter. It can iterate and have functions with more parameters. And it also doesn't have to be strict. I mean, as we see here, this is polymorphic. This is actually, I don't know whether the slide says something to that. This wouldn't work automatically. Then quick check would pick a type. I think it would pick the unit type in this case. So I can also do quick check append length. But then it, because it doesn't know for which type to test this, so it doesn't pick an arbitrary type. So by default it will pick the unit type. And so we get this warning here. But I mean, that also seems to hold, at least for the unit type. But we could do it for another type. For example, we could say this by giving a type on annotation. So for example, list of strings to bool. Then it actually does it for list of strings. Right. So it works for much more general situations than just our running example. A function of one int list argument. So it can be basically arbitrary many arguments. And it also works for no arguments, which is a classical unit test. So quick check in particular can do normal unit tests. So for example, we can have a property length empty, which is just of type bool, which says that the length of the empty list should be 0. And we can also test that with quick check, and then it says pass one test. So in this case, there's nothing to randomly generate. There are no free parameters to the function. So it just checks whether that Boolean is actually true. And if I made a mistake there, then it just says it's false. It's not true that it's true. So the point of that is to, this case recovers classical unit test that you are probably used to. It's just a property. Nothing needs to be randomly picked. It's just a statement. I mean, that's, so quick check in particular can do classical unit tests, but it can do much more because it can generate test cases for you. So to understand what this class testable means, after seeing all these examples, we can now say that testable properties are usual functions with arbitrarily many arguments resulting in a bool. So we had basically no argument, and our initial examples were one argument, but we also saw now with this take drop 2 arguments, and this drop twice even 3 arguments. So all of these can be tested with quick check, and normally it looks like this. And now, of course, what arguments can we use there? And the answer is no, because obviously quick check somehow needs to know how to generate random arguments. I mean, so it only works if all the arguments, I mean, it knows how to do this. And quick check does that with right. Okay, and so basically this is how it's defined, or how it could be defined. I actually don't know whether quick check actually defines it like that. So testable is a type class for some type prop. This property you can think of as like generalization of Booleans. So it's like Booleans on steroids, where it can give you nice information. So we will see that later. Don't worry about it so much. So basically the base case is that bool is testable, so just unit tests. And then if B is testable, then functions from A to B are also testable, provided A is showable, because we saw when it finds counterexamples, it always prints the counterexample on the screen. In order to be able to print that, it must know how to print that argument. And then this thing we haven't seen yet, arbitrary. And that is a type class we will look at next. That basically says, I mean, if type A is an instance of arbitrary, then you can generate random A's. And this is basically the inductive case, and then together that leads to all the examples we have seen. Right. But before we come to, let me see. So there is something, I mean, until now we used quick check, but there's also something called verbose check. Maybe we should see that, or try to see it in action. Let me just, I honestly don't know what it exactly does. Let me just reintroduce this, or let's use this take drop, drop twice, sorry. You know drop twice is, so if we do quick check drop twice, then we get this, let's try this verbose check. Okay, let's make this bigger. Right, so with verbose check we see what it all tried. So first it tried it with these 3 and that passed. And then it tried it with this and it failed. And now it tries to shrink to make this simpler. So first it tries to make the 1 simpler, but that passes. Now it tries to make this, so yeah. So basically already in this example, the second thing it tried was already a counterexample, 1 minus 1 minus 1. But now it tries to shrink that to make it a minimal counterexample. And the way it does it in this case, it first tries to make this 1 simpler. And to make a 1 simpler, quick check tries a 0 instead. But it turns out if you do it with 0 minus 1 and list of minus 1, it actually is true the property. So it can't make this 1 simpler like this. So then next it tries to make the minus 1 simpler, and it turns it into 1. but that unfortunately also passes. So last it tries to make this -1 simpler, and that also passes, and then it tries different ways to make these things simpler, and eventually it finds a simpler way where it has now returned, it has replaced the -1 here in the list with a 1. And then it goes on and on. I mean, the details are not important, and now it has turned the 1 into a 0, and that's probably it, yes. And now it can't make this any simpler anymore. So in this case, it will give this counter example here. So basically, I mean, the details are not important. Point is just with this verbose check, you don't only see the final minimal example, you see all the examples it tried in between to get to this final minimal example. So that's one way to get more information. Okay, and often this is too verbose, and actually we didn't see this now that it gets bigger and bigger, so maybe, I don't know, we will see that later. Let's just see. So there's right. So there's another, I mean, often, I mean, in order to gain confidence about your tests, I mean, it's important to understand what type of random data it actually generated. And sometimes, I mean, it turns out in more complex situations that you, I mean, so it can put you in a false sense of security if everything passes, and that sometimes the case can be that the test cases it generates are just too simple. So it's good to get an idea of how complex they are. And one way to do this, I mean, it's this verbose check to see what examples it tried, but that's often like lots of stuff, lots of screens, especially with more complicated examples. Another way is there's a function collect, so it takes a testable property and something that's showable of type A, and so basically, and it sort of labels it with this. So there's this example. If we try this, so now we want to check for this sort preserves length function. How often is the list we are actually trying it with the empty list? So in this case, we use A for type Boolean, and the A we use here is we check whether the randomly generated list is empty. And then we do the usual test, the sort preserves length. So let me do that in the REPL. So quick check. So now so earlier we had just basically, I mean, we had sort preserves length, right? And that passed. And now let's say we want more confidence that the lists it tried it for are actually reasonable, not just the empty list. So now the idea is I could do basically, instead of, I mean, this is, as I explained some days ago, this is the same. And now I can, instead of doing this directly, I can use this collect and put some sort of label here. So on the slide it's null. And now that says 7% of the 100 test cases that were tried, so it was 100, so 7% is 7. So 7 times it tried with the empty list, and 93 times it tried with a non-empty list. So now I have like more information. I mean, of course I don't have to use null, I can use any showable things. For example, I could obviously use length. And now I see, I mean, this is now a bit, I mean, maybe not a good idea to use length. I mean, there are other ways to do it.
To reduce maybe length, but maybe.
Yeah, I can do whatever length modulo 10. No, not modulo, divide, div 10, sorry, div 10. So for example, this would now tell me in 34% of the test cases it was shorter than 10, the list. In 20% of the test cases it was shorter than 20, but longer than 10 and so on. And 1% of the test cases it was like 90 elements. So it's just an example. that QuickCheck provides like more tools than just this simple QuickCheck function to give you to help you get an idea about the distribution of these random test cases. Let's see. So we tried this. Okay, tried that. Huh. Oh, cool. Right, and this property thing, as I said, that's like a Boolean on steroids. So it somehow, I mean, it's not important. You can think of it as Boolean. And okay, we can find right, let's try this. So let's define Boolean implication. So implies pool implies xy is y or not x. Yeah, okay, here's on the slide it's the other way around. Let me also do it. I mean, this is a classical definition of implication, logical implication. So if I have a premise and a conclusion, then the premise implies the conclusion if either if the conclusion holds or if the premise is wrong. Anyway, but that's only a helper function, and now we could, for example, say insert preserves ordered, which is a nice. Remember we had this insert function, and we only until now wrote tests for sort, but of course we could also try to test insert directly. And one reasonable property is that if you start with a sorted list and then have a new number and use insert to insert it, then afterwards the list should also be sorted. And we can, so that's a property from int to list of int to bool. And it would state that if the list is already sorted, so is sorted access, that would imply that also after inserting x into the list, it's still sorted. Okay? Let's try this. Sorry, this should be a no, it's all good. It's only because of the large font, it's better to put it like this. So let's try this. I mean, it should hold actually. Quick check. Because we believe now that our implementation is correct. Right. But this is now a typical case where maybe where this is a false sense of security. And can you imagine, can you imagine why this is maybe not a good property, the way it's written now? Even though it's correct. It's definitely correct and this should hold. But nevertheless, it's not a good property. And can you imagine why? Yes, sure. The problem is that, as we saw, how does QuickCheck work in this case? It will generate 100 times, it will generate a random x and a random list of ints, and then we'll check that this holds. But because of how implies works, so it will first check whether the original list, the x's are sorted. If they are sorted, it will then it must check that also after inserting X, it's still sorted. That's the interesting case. But if XS is not sorted, then the implication is trivially true. Then we are in this case here. So that means if QuickCheck randomly picks a not sorted list, then it never needs to like evaluate the insert, the function we're interested in, because then it's trivially true. And of course, if you pick a random list, especially a long random list, then chances that it will be sorted are not very high. So probably most of the cases it will try. The XS will not be sorted, and it doesn't actually test anything. And we can of course use collect to make that precise. So we can use collect is sorted XS, insert reserve sorted XS. And we see that of the 100 test cases, only, 90% were unsorted lists. And in those 90 cases, because this was false, we never had to check anything there. And only in 10 cases was the first list sorted, and then we checked something. And chances are that of these 10 cases, probably 5 of them were the empty list or something. Because chances are higher to randomly pick a list that's sorted if it's a short list. So this it creates a false sense of security, because you think it tested on 100 random lists, but actually it only had like 10 relevant cases. Of those, probably a lot were very short. Okay? And but QuickCheck comes to the rescue. Okay, here you also see it's random. When we did that for the slides, it was not 90-10, it was 88-12, so it always depends. It's like new randomness each time you run it. But there is something in QuickCheck which looks like implication in mathematics, so it's this double equals error, so that's QuickCheck specific, and that basically is, it behaves like our implies, but it behaves differently. So we can, if we just replace this with this arrow, sorry, there's something wrong now. Okay, now this is no longer a Boolean, this is now a property, but as I said, that's because this random error, if you look at the type, it produces a property, not a Boolean, but you can think of a property as of a Boolean. So I just replace this reply with imply with this error from the QuickCheck library, and now if I run it again, now there's a second problem. But now it works differently. So what does this error mean? So semantically it's the same. So it also implies. So it's exactly as before in that sense. But now QuickCheck behaves differently. Earlier it just generated 100 XS pairs and evaluated this on the implies. And then basically 90 of those were useless. But so we ended up with only 100 useful ones, 10 useful ones. So this implies, this arrow behaves differently. So now it will start generating and then evaluate the left-hand side of the arrow. And if that's true, then good, and it takes the test case and checks the right-hand side. But if it's false, it won't count that for the 100. So it will try the next random sample. So it will try to find 100 random cases where this is true. So that is good. That's what we want. But we see now this year passed only 76 tests, 1,000 discarded tests. So that means it managed, it tried 1,000 things, and of those 1,000 random pairs of X and XS, it only found 76 where this held, where the XS was actually sorted. So it tried 1,000 and then gave up. You can somehow configure that. You could also try 10,000 or so. But the problem is it's so unlikely to I mean, so this is now better. I mean, earlier we basically had 10 relevant tests, now we have 76 relevant tests. But we wanted 100 or 1,000 or so. So now the problem is that it's just, I mean, very difficult to pick a random list and hope that it's sorted. So, right. In this, so here it already gave up after 41 tests on the slide, so that's not right. And we can come to this later. I mean, we can revisit that. But now let's first talk about generators. And there is this type class arbitrary that I just mentioned a couple of minutes ago. So the intuition of arbitrary is that it means that QuickCheck knows, or I mean, you know how to generate arbitrary random elements of type A. And this Gen A type is something like a plan or a prescription how to generate random A's. So don't worry about it too much. It's opaque anyway, I think, in the QuickCheck library. And let's first play with it. So there are, I mean, or often when you use QuickCheck, you want to get a feeling for your generators and you have to write generators. So there is this sample function. So for a showable type A and a generator, we can use sample, and then it just prints, I think, 100 randomly generated A's on the screen. So we can get a feeling for the distribution. So let's try this. For example, let's try simple with whatever, with int, let's say. So sample. So now we need a generator, and we have this arbitrary class. So arbitrary is a generator. But now the compiler can't know what type we mean, so we say that. So let's start with int, for example. Oh, it's only 10 or 20, or whatever. So now basically QuickCheck uses this arbitrary instance it has for ints, so that's built into QuickCheck, to generate, what is it, 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 random ints, so we get a feel for what type of ints it generates. And there's a, as you can see on the slides, there's a sample prime, which instead of in IO printing the random numbers to the screen, gives you a list of random numbers. And you also see it's now different list than what was. So that's each time like different. It's not reproducible or deterministic. But I mean, we already see somehow it starts with 0. And then the numbers are smallish first, and they tend to get bigger, even though there's the 5 again, so it's not like monotonic bigger, but okay. And I mean, we can do this like several times, and we see that it like always starts with smallish numbers and gets bigger for int. And we can try it for other types. I mean, QuickCheck has lots of instances for this arbitrary. So for example, I mean, what we used all the time was list of ints. So let's try it for list of ints. Okay, and we see also that it starts with, with the empty list and very shortish lists. And these lists contain relatively small ints. And then over time, the last examples are longer and the numbers also get bigger. And there are lots of types that have an arbitrary instance. So for example, I mean, Boolean. Of course, that's somewhat boring because there are no, I mean, there are only 2 possibilities. Or we could try character. So we see it tries, I mean, all sorts of like weird characters as well. What else could we try? I mean, double.
Pairs.
Sorry?
Pairs.
Pairs, yes, exactly. Right. Or now that we know that it works for ints and booleans, I mean, we can, for example, try pairs of ints and booleans, or maybe ints and ints. Right, and again we see for the pair stuff it starts with relatively small numbers and later they get bigger and more complicated. And we can of course also ask for information on arbitrary, and then we see some instances, and that's a long list. And a lot of those types we don't know, but I'm sure somewhere here, for example, we have our old friends like int and float and double, character, bool. Then we have rules for pairs and triples, and list will also be somewhere there. So basically QuickCheck already, without you doing anything, knows a lot about generating random numbers for like most common types. I mean, triples also work, so we could do bool character, and it would generate random triples. So far so good. But of course often you have custom data types like our blockchain type in the first lecture or whatever, or binary trees, and then obviously QuickCheck can't automatically know how to do that. So in that situation you have to write your own random generators if you want to test properties for types that involve, for functions that involve those types. And there are a couple of like combinators that you can use to build generators. For example, choose. Random is a type class that we haven't talked about yet, and it's I think it's also in somewhere that is not even, no. Anyway, that's not important. It's in the base libraries, or no, it's not even in the base libraries. It's something called random, but it basically means that it's known how to generate random A's. And or again, all the base types like int and character and word and so on are instances of random. So one combinator we can use is choose. Although somehow I'm a bit confused that it doesn't. It's a bit weird that it doesn't demand that it's ordered. I mean, I have no idea what it does if it's not an instance of ord. But whatever. The idea is it basically picks something in this interval. No. Sorry. I thought it would, but maybe it just picks one of the two?
Generates one random value in the range from A to A.
Yeah, but what does the range mean if it's not odd? Maybe random implies odd? Or something.
We can check that.
Yes. So anyway, apart from that, the idea is it picks in a range. So let me do the sample again of choose, and let's, whatever, a die, right? So let's go from 1 to 6. And now we see, indeed, I mean, I can do it several times. So it always now generates elements ints between 1 and 6. Or I could do the same for double, for example, only doubles between 0 and 1. So I could do this, and now hopefully I only get doubles between 0 and 1. So that's one way to like get a new generator, a specific one. What else? One-off. So it can randomly choose between different generators. So for example, I could do sample one-off, and let's pick, I don't know, choose 0, 1, and choose 99, 999. That's whatever. I mean, it doesn't matter. So now it will basically, I have given it two generators, two chooses in this case, and it will basically with 50-50 probability pick one and then use that one. So about half of the examples will now be between 0 and 1, and the other half of the examples will be between 99 and 101.
About the OR thing,
yes?
There's no requirement for OR because the concept of range depends on the type. Not necessarily it has to be the same thing. So that's what I do.
Okay, fine. But of course, random. I mean, random already has this random R. So yes, yeah, that's okay, right. Anyway, so this is one way. So if you have several generators, you can pick randomly between one of them. And okay, what next? Frequency. So that is like a generalization of one-off. So again, a list of generators and picks one of them, but we can weigh them differently. So I could change this example here. Instead of one-off, use frequency. Sorry, the int comes first. And let's say I weigh this 0, 1 with 1. And I weigh this 99, 100 with, I don't know, 3. And now the samples that are between 99 and 101 should be 3 times as frequent as the ones between 0 and 1. Or I could, of course, do it the other way around. I mean, it's hard to see with so few samples whether it's true, but okay, that's that. And I mean, you don't have to like learn it by heart. It's just nice to know that it exists. Elements is very simple. So you just give it a list and it picks a random element from the list. So for example, I could do sample elements ABC, and now it would randomly, I mean, the generator would pick one of A, B, or C with equal probability. So like this. Right, and sized. Well, sized, I mean, we saw, I mean, what can I say? I mean, we saw it's not just about picking random elements, it's also about making them increasingly more complex. So we saw it always starts with simple ones and makes them more complicated. So this gen type is a bit complex. It's not just about randomness, it's also about this complexity. And one way to make that, and basically if you use sample or if you run quick check, then it starts with size 0 and slowly increases the size. And the expectation is, I mean, these arbitrary instances, these generators, they should then, if the size becomes bigger, produce more complex samples. And normally the size is implicit, so you don't have access to it. But using this size function, you can explicitly get your hands on the size. So for example, we could do sample sized. So now we have the size, let's call it n. And now I can do something with the size in terms of generator. For example, I don't know, I could say if the size is less than 5, then I want an A. And else I want X, Y, or Z capital. And that won't work, and that's also bad. Let's also do elements. Right, so now we see basically in the samples it starts with small sizes. So first 3, it seems the size is less than 5. So it picks the first generator, and then sizes are bigger, and then I said, okay, then take one of the 3 X, Y, Z. So that size is used often because, I mean, if you write your own custom generators, you are supposed to also respect that some of the size is taken into account. And I think it's a good example or a good idea. Let's see. Right, and for like simple types that only have like finitely many elements, for example, Boolean, I mean, that's already built in, but it would be very simple to write, I mean, using elements to just write a generator, which just picks uniformly one of the elements. So if you have whatever, deer, I think we didn't have that as an example. So if you have a type for the compass directions, north, east, south, west, and you wanted to write an arbitrary instance for it, you could also use elements. And then it would just randomly pick one of the 4. So that is simple. And generating numbers, I mean, it's also built in, but one could use this thing with this choose. So you could say, you could implement the arbitrary instance for int to choose randomly an int between -20 and 20. But it's better to use the size. So this is more, closer to how it's implemented. So basically with increasing size, it allows to pick larger integers. All right. And I think before I do this, let me just see what comes there. Right, before we go there, I think I want to give another example that's also about binary trees. I think it would be a good idea to show binary trees, how you would write a generator for that, because this goes into another direction. So let's to get a feeling for this. So let's repeat our type tree A. It was either a leaf or it was a node with 2 children recursively. And let's just deriving, I don't know, at least show for the time being. Right, and let's say we want to make that an instance of arbitrary. So first of all, that can't possibly work because, trees have leaves, and if we want to generate a random leaf, then, the leaf carries something of type A, so we must know how to generate random A's in order to do this. So we definitely need a superclass arbitrary A, and not superclass, as a condition, we need this. So the leaf type must be arbitrary in order to do this. Okay, so how would we do that? The first approximation, I think, first of all, we have 2 constructors. So we could, pick one of them randomly. So we could do, what was it, 1 off? So now we do 2 generators, one for leaves and one for nodes. And pick randomly one or the other. Okay, so how would we do leaf? And right, so let's say, okay, hang on, sorry. I haven't planned that beforehand, so I must improvise a bit. Let's call it gen leaf. It's no, sorry, let not annotate it. So that's supposed to, and gen node. So I want to pick between those 2. Okay, now we have a problem. Just to generate a leaf. We now know how to randomly generate an A, but how do we use that to generate a leaf? How do we get the leaf constructor applied to this? And there we are in luck, because if we ask for information on gen again, then we see many scary things, but one is functor. And functor we know. So in particular, we know that we have fmap. So if we have something from A to B, then we have a function from gen A to gen B. So if we apply this to the case that A is A and B is tree A, then we can fmap, so we can do this, hang on. We can fmap tree, not tree, leaf over arbitrary. And maybe I should, so I would write this like this. So maybe I should somehow explain this. So fmap for functor, if we have a functor f, then given something from A to B, map something from FA to FB. That's the definition of fmap. So if we now specialize that for gen, then we have something from A to B. It gives us something from gen A to gen B. So now if we fmap leaf, so leaf I mean, if I annotate that, so leaf goes from A to tree A. So this now goes from gen A to gen tree A, which is exactly what we want. And now gen A we have arbitrary. So we have fmap leaf arbitrary goes, I mean, is of type gen tree A, which is what we want. So it just says, okay, we generate a random value A, and then we can fmap the leaf constructor over it to get to a random tree. So this is taking care of leaves. So now in 50% of cases, we get, I'm just trying desperately to think how I do this now. It's a bit icky. Right, so we can generate leaves. And now the node case is a bit, maybe I shouldn't have done this example, but we need it anyway. I mean, lift A2, I don't know, because I have to, or I could do, I'm sorry?
Where is so leave them? So we can use leave them too. Or what's you?
No, my problem is that for node I need like applicative or monad or do notation or something. But what I could do is just a second. Maybe I shouldn't have done this example now, but it's needed in the exercises anyway. And I mean, if you don't understand it today, tomorrow you will understand it. So don't worry too much.
One more day.
There is, let me just, I think I have to, so don't worry about it too much, please. But we saw when we talked about I/O, we saw this lift m function given two I/O actions, and a function and two I/O actions, how you can basically run both plans and then combine the results with the given function. And it turns out that this is more general. It doesn't only work for I/O, it, for example, also works for gen. So I mean, what I want to do in the node case is to randomly generate the left child, randomly generate the right child, and then combine them to a tree with the node constructor. And I can do this, so don't worry too much about it. Like lift m2 node arbitrary. So this at least compiles. So basically it generates random tree, another random tree recursively. I'm just defining arbitrary. And then it uses this lift m2 to combine them with the node constructor to a random tree that has the first randomly generated one as left child and the second randomly generated one as right child. And the problem now is that we can try this now. I mean, we can do sample for arbitrary type gen tree whatever, let's say int. And now that even worked. So that's good. Can try it again. Right. But so it does work. But the problem somehow is that the trees get very big very quickly. And that is because we don't take good control of the size. We somehow, it basically grows exponentially. I mean, so the trick here is, I mean, the point is often with recursive data types it's not so easy to generate a good, I mean, to write a good arbitrary instance. So what we actually would like is to somehow, I mean, and what this size parameter means is up to us. So I mean, I mean, nowhere is written what is a tree of complexity 7. I mean, we can decide that. But I think it would make sense to say it should be the maximum number of leaves in the tree. Maybe +1, because I think the size starts at 0 and there is no tree that has 0 leaves. So maybe we okay, so I mean this works, but the problem is that it generates like really big trees very quickly. So only for like small sizes, they are like ridiculously big trees. And that would be bad because, I mean, this is sample, as we saw, only generates 11 samples or something. So the size is like 10 or something. But quick check, if you run it on 100, it will get to size 100, and then the trees would be really, really big. So somehow we must control the growth of these trees. So the idea is that we somehow, I mean, first of all, we must decide what should be the size. I mean, it's up to us, but let's say a random tree of size n should have at most, let's say, n plus 1 leaves. And it's the n plus 1 is just because the size in QuickCheck starts at 0, but with our tree type, there is the empty tree is not a value. I mean, because we have a leaf or a node, and so we always have at least 1 leaf. So there is no tree that has at most 0 leaves. So therefore, I just set this n plus 1. And then now we should maybe write a helper function. Whatever gen tree or something that gets an int, that's the size, and generates a tree. So the idea is generate a random tree with at most the given number of leaves. Okay, and once we have this helper function, then we can write our arbitrary instance nicely by saying size, that's this thing we had earlier, and just use this function gentree on n plus 1. So that's the strategy. And something like that you often have to do if it's like complicated recursive types. And this, even though the types are scary, is, arbitrary A. It's relatively simple, so we can just say, okay, if this n is less than or equal 1, then all we can do is a leaf, because a node has at least 2. So we just do what we did before, leaf and fmap it over arbitrary. And otherwise, yeah, now we have like several strategies. So this is now also a bit awkward. I think I shouldn't have done this. I mean, for example, we could diff by 2 and then recursively do it for half the size. I mean, it would be better to pick a random one, but then it's like do notation and it's horrible. Right. So one thing we could do is, so we again lose this lift m2 node, but now we do gen tree. Let's define m as n divided by 2 and just do it like this. This is not like ideal, I think, but it should work. I mean, they are smaller now. It's still, I mean, we don't get these crazy big ones anymore. 2, 1. Yes, I think it's right, yeah. So now we get like reasonably sized trees. And of course, one could tweak that. But yeah, that's just an example. But you will understand that much better tomorrow, so don't worry too much about it. Right, I don't know, should we have another break?
What constraints?
Sorted lists, how to write a, because, yeah. And then let's see, sum for all. Okay, then these modifiers. And then we're almost done. So maybe one more break and then it's not much anymore. Okay. So this is also a bit of an art to write these arbitrary instances. So you don't have to worry too much about that. But there is one exercise in the homework for the first week. Yes, there's permutation, then there is a data type that's, I mean, not trees, but it's what
probably the last individual assignment. On top of that, we'll have weekly group assignments, and this week we will publish tomorrow. So if we want to start discussing about forming groups, ideally less than 4 people, and the process will be the same as individual assignments. You will get to click and you will get to select the group that you belong to, and that's it. So there will be more fun, and more complex and fun to play.
Okay, that's a second. Okay. I just wanted to say that this generator that I wrote really is not good because it always produces balanced trees. Balanced trees. Because if you see how it works, for example, if I want to generate, if I use this gen tree for 6, then n is 6, so we are in the second case here. So then I will recursively call it for the left and right child with 3. So for 3 we are again in the second case. So for the grandchildren of the root I will recursively call it with 1. Then we are in the first case. So I will always get a tree with exactly 4 leaves, and it's like perfectly symmetrical. So that's not good. So what I could do, for example, is I could use this one off here. So I use this, what I have, but I can also just do this leaf arbitrary. And if I do that, then it should look more, must reload. So then I get like, I mean, then it's more heterogeneous. And now maybe that's a bit extreme. I mean, I could also use this frequency. Let me just reformat this. So instead of one off, I could use frequency and then, I don't know, use leaf with weight 1 and whatever, node with weight 2. And now it's like not so many leaves anymore, but also not so symmetric. But that's still not ideal. So I think tomorrow, after tomorrow's lecture, we can revisit this and do it like nicer, that we really get random trees. That because now the problem still is that because of the second case, if we generate a node, we will always divide this n by 2. So we will never have like a totally skewed tree where almost all the nodes sit on the right child and only one is on the left child. It will always be at most half of the size on both sides. So it's better now, but still not perfect. Yeah. Anyway, let's go back to the slides. So we have that. And now let's recall the problem we had. We wanted to check this property that if you insert into a sorted list, it's again sorted. And our first try was with our own implies, the Boolean implies. And then it passed, but the problem was that most of the test cases we generated were useless. Because, so we thought we had tested it for 100 lists, and we had, but 90 of those 100 lists were not sorted, so the thing we were actually testing was trivial and didn't even invoke our insert function. Right, and then we used instead this equals arrow operator from QuickCheck. So that fixes that problem. So now all the test cases will be relevant. It will only test it for sorted lists. But then it gave up after 1,000 lists because it's so difficult to just take a random list and hope it's sorted. So that's better, but also not good. And now we want to fix this, and the idea is just to write a specific generator that just generates sorted lists. So I mean, and until now we basically generated sorted lists by generating a random list and checking whether it's sorted and throwing it away if it's not. But of course it would be better if we could somehow just only generate sorted lists. And this, I mean, this is not particularly important, this function. Sorry. So the idea is to write a function that takes a list of ints and produces a sorted list of ints, and that is somehow simple. And so what it does is it maps the empty list to the empty list and the list with one element to itself. And the list with more than one element. It keeps the first element, but then applies it recursively, but it does this. And as I said, that's somehow a clever trick, but it's not important, and you could do this differently. I probably would have done it differently. But I mean, you can think about why that works. The point is just that it's a simple function that's fast, and it just turns an arbitrary random list into another random list, but one that is sorted. So we can just try it out. So make sorted, we take some arbitrary list, and it generates a new list. I mean, also the elements are not the same or anything, but it's sorted. And as I said, I mean, the particular implementation of this is not important. What is important is the idea that we have this problem that we generate too much that's useless and throw away almost everything. So instead we somehow modify what we generate to be useful for us. In this case, be sorted. And now the question is, how would we use this? Because right now we only know how to use things that have types that have arbitrary instance. I mean, one way, of course, would be, I mean, we could use it already. Maybe I should actually show this. So one way to test this, what was it? Insert preserves ordered. This is now not on the slides, but I mean, one way we could now make use of our sorted function, make sorted is we just apply it to this random list of x's, and then so we don't need this premise anymore because now the ys is sorted, and we just check that. Why is this now? Right now it's bool again, sorry. Right, so this would be one way to do this. So we still generate random x and random list of integers, but now instead of hoping that this is sorted, we just apply our make sorted function and then check the property we're interested in for that. And that should now work. Quick check, insert, for that. Ticked, yes. Right, so now this is one way. And that's perfectly fine, I think. But there's also another way, if we go back to the slides. So I mean, we can write another generator for ints now. So I mean, using this. So gen sorted. It's a generator for int lists. And I already told you that gen is a functor. So we can just fmap our make sorted function over arbitrary. So let's try this. So now if we sample the original arbitrary for int lists, then as we see, basically of these, I mean, we see the problem here, that of those almost none is sorted. I mean, the only sorted one I think is the empty one at the beginning and in the middle, and all the others are not sorted. So that's the problem, why this generator is bad for this property, because we throw away everything. But now if we instead use our new gen sorted generator, then we get nice random lists, but all of them are sorted. So it's much better for this case. And of course now the problem is, how do we use this for quick check? Because until now we only know how to use arbitrary, not arbitrary generators. But there is another quick check operator for all that takes a generator for A's, the function from A to B, and if B is testable, then we get the property. So we can basically rewrite this here in a slightly different way now using this gen sorted. So let's call it whatever, insert preserved order double prime. So this now again goes from print. This now goes from, let's keep this first. So given x, random x, so we now use this for all, and our gen sorted, and now this is a sorted list, and now we can do what we did before. Sorted, insert xxx, and now this is property. So this is a way to use like custom generators. This for all, so that's built into, and that should again, I mean, do the same thing. I mean, should pass. So if we do quick check with double prime, it also passes. This is very similar. Basically, under the hood, it more or less does this here, what I did by hand. And then there's another technique that's very useful, and that also outside of testing, just in general for dealing with type classes. I mean, often you have the problem that the thing with type classes in Haskell is that a type can have at most one instance for a type class. So, I mean, either you are showable or you are not, but there can't be two different instances for showable. And that has very nice properties, so that allows Haskell to like figure out instances automatically and so on. But sometimes it's also not really ideal, because sometimes we would like two different instances for something, but that's not possible in Haskell. But what you can do is you can use a new type instead. So that's one of the prime applications of new types, to write different instances. So for example, we could do define a new type, whatever, sorted int list, and that's, remember, a new type, it must be a constructor, I mean only one constructor with one argument. And now the point is that even though int lists already have an arbitrary instance, so we can't change that or add another one, we can, for new types, nobody stops us from generating a new one. So we could now do instance arbitrary sorted int list, where arbitrary is this new constructor here, f mapped over our gen sorted. So now if we have this, then we could do a fourth version of this here. I can just write it. Which now goes from int and sorted int list to bool. X, so now we pattern match against this to get our underlying list out, and now it's the same again. That is sorted insert x-axis. Ugh. I must reload. Insert preserves ordered. I didn't save, sorry. Now. Yeah, okay, so that also works. And that's maybe even the nicest way to do this. So always many ways to skin a cat. But, right. And incidentally, you wouldn't have to do that at all because QuickCheck already does that. So I think it's called ordered or ordered list. So that's already in QuickCheck. So QuickCheck has that, and not only for int, but for arbitrary types or arbitrary orderable arbitrary types. So we wouldn't even need our custom type. Sorry, let me first demonstrate. I mean, first of all, I could also demonstrate this with sample. I mean, it's always a good idea to use sample to get a feeling. So with my sorted int list, so if I do sample arbitrary type gen sorted int list to convince ourselves that it works. So it indeed generates like sorted lists. I mean, it's the same thing as before with the gen sorted, but now it's arbitrary. But we wouldn't even need to do that because we can just use the built-in QuickChat thing that's called ordered list int. And that does exactly the same, basically. So QuickCheck already has that built in. So we could have a fifth version of this. Where we don't use our custom type, but this ordered list int. And then the constructor has a different name. I think ordered. Yeah, so the constructor is called ordered. And that should again so one more tick, yeah, that still passes. Right, so this is a nice trick, and as I said, not only in the context of testing, in lots of contexts. And QuickCheck doesn't only do that for ordered lists, it has it for other things. So if we, so this ordered list thing is what we just looked at. QuickCheck also has these new type wrappers for positive numbers, non-negative numbers, non-zero numbers, non-empty lists, and so on. So always the same trick. So for example, if we, I mean, again, if we use the gen for int, then we get the empty list quite often. But if we somehow don't want, then we can use this non-empty list. So instead of int, we can use non-empty list int. And then we see it doesn't generate an empty list anymore. Or, I mean, if we use the gen int, we get positive and negative numbers, but if instead we use the, for example, positive new type wrapper, then we only get positive numbers. Or if we use the non-negative one, then we do get 0, but still nothing negative. And if we use the non-zero one, then we get positive and negative, but no longer 0. And that doesn't only work for int, it works where it makes sense. So for double it would also work, or for word, or for integer. So yes, so QuickCheck has all sorts of these new type wrappers to make it for common cases, because often you want to test something with whatever. I mean, only positive numbers, for example, then, I mean, for example, we could probably fix our, I mean, there was this property with the drop that failed. What was it called? Drop twice. So quick check, drop twice. We get this counter example with -1, 1. But our hypothesis, of course, could be that the problem is the negative number. And maybe this property actually is true as long as m and n are not negative. So we could, let's call it for non-negative. I mean, it should be true, I suppose. And I think this should now hold. Or maybe I'm wrong. What now? It's a bit strange.
Because you try to run the function alone without the quick check.
Oh, sorry. Of course. Right, so this seems to hold. So the problem why this, I mean, this should be true somehow, dropping m elements and n elements should be the same as dropping m plus n. And it wasn't true, but the problem is really just, it seems, negative numbers. As soon as we go to non-negative, it probably holds. Yes, so these things can be useful for quick check. So now that's that. Right. And I mean, you should really use quick check. It's really cool. And it's, I mean, every other programming language is very jealous that Haskell has that. And it's so nice. And I mean, it's really powerful. Of course, you need practice to use it. But it's really fantastic that, and I mean, now it was always 100, but I think in production one should use 1,000 or even 10,000, and you can configure that, and it's really powerful, and it finds a lot of like edge cases, because this random test generation somehow, I mean, it tests things that humans, I mean, writes tests that humans normally wouldn't try, and often it finds edge cases that a human would have overlooked. So that's really a powerful tool. There's of course much more to say to it. I mean, at IOG we have had some years ago a workshop for all our Haskell developers with John Yu himself that basically taught us how to properly use quick check, and so it's a very interesting subject. And of course, I mean, so yes, what we have seen, so you basically can write properties like for all, I mean, that with free variables, so to say, like an arbitrary list. And then the test data is automatically and randomly generated. There's also, as we now saw, a way to write your custom generators. And yes, you should use it. And then there are also other, I mean, in the beginning I mentioned other libraries, testing libraries. So, I mean, you should also try those. I personally haven't used small check in Hedgehog. So the small check is, instead of randomly generating data, it somehow generates all possible cases, but only up to a certain size. And Hedgehog, I think, is similar to quick check in principle, but there are like some subtle differences that probably you wouldn't understand right now. And somehow how generation and shrinking works together is different in Hedgehog. And right. Yes, and keep in mind that, of course, writing good tests is also an art. And as we saw in this example, that tests can have bugs too, of course. Right, and the last topic for today is program coverage. So there is a way to, but the problem is I somehow need a test suite for that after all, and I don't know how to get one quickly. A test suite. Maybe I...
You want to create one now, or maybe we can show this tomorrow?
Yeah, maybe we should skip this and do it tomorrow. Because in order to use it, I need a test suite. And as we saw at the beginning of this lecture, I mean, that didn't work. I was thinking too simplistically. So then maybe until tomorrow I can add a proper test suite to this example, and then we can cover the coverage tomorrow. So there's a tool that comes with GHC if you have tests that basically shows nicely in HTML, nicely formatted with colors, which parts of your program are covered by the test. So that's of course useful. But I think we would need a nice example for that, and we need a proper test suite. And I wanted to show that to you anyway tomorrow, how to do that. So then let's do that tomorrow. Yeah. So then I think we're done for today, except if you have questions. And tomorrow we'll also better understand this binary tree example. Yeah. So don't worry about that now. And you should really watch this video. Maybe we really must find the link on, hang on, maybe I can find it now. Computer file John Hughes.
Yeah. I think if you search quick check computer file.
Probably this one. It's only 10 minutes. Can it be so short?
We're going to look at an example of property-based testing.
Yeah, that's one. So if you just Google computer file John Hughes, that's him, by the way. So I think he's from Wales, but he lives in Sweden. He's a professor at Chalmers University, I believe, in Sweden. So yeah, he's one of the great ones in the Haskell world. A very nice guy, very friendly. And he, as I said, this is not Haskell, it's Erlang, I think. I mean, in principle, you could watch it now together, but I mean, you don't have to. I mean, it's only 10 minutes, so you really should watch it. It's very nice. How he has something that actually happens. I mean, it's a real bug in SMS specification or something. So he shows something wrong in phones where certain things don't properly work and where it doesn't follow the specification. And he basically finds the problem with quick check and narrows it down, and basically in the end he finds the bug by just using quick check. And
I'm not sure if that
maybe that's the wrong one.
Yeah, maybe, but I think that's more like an overview.
Okay, there's another.
We could find it.
Should I say quick check? This one, that's 40 minutes. But that's a talk, that's not computer file. He also talks about testing smart contracts. There's also, I mean, that's specific for Plutus, for example. Yeah, we can look it up until tomorrow. But it's very nice, it's very cool how he finds the error, and yeah. So you should really use it. And I mean, in principle, with Haskell, one can also do like test-driven development. I mean, I personally have never really done that except for fun, to try it out. But in principle, you can write your tests first in form of properties and then develop. I mean, John Hughes even propagates that you, that you really do this, and that you start with very simple properties, and then that it evolves together. So, I mean, you basically start with 0 tests, and I mean, then something, I mean, you have an obvious wrong implementation with the simplest possible implementation, and then you come up with a property that invalidates, that says this implementation is invalid, and then you do the smallest possible fix to make the property pass, and then you refine the property, make it better, and so on, so back and forth. That's actually fun to try that. Yes?
So, quick check, is it what I'm kind of getting is it basically tests like it's for the pure side of things. So is that correct? And if not, can you use it to test like inputs, reading files?
It's correct that QuickChat itself is only for pure things, but there are other libraries, even some written by John Hughes himself and also by other people, that extend the same idea to I/O. So you can actually test stuff like read file. It's also one of the standard examples. And the idea basically is, if you want to test I/O, you generate random traces. So let's say you want, one of the exercises he did with us when he did this training for us was like a file system. So we wanted to test something like open file, close file, read file, write file, and that works as expected. and then you generate like random sequences of events, like create this file, open it, write to it, close it again. And so basically the arbitrary instance, it generates like these sequences of actions. And then basically once you have such a sequence of actions, you need a model what should happen, like a pure model, but you also run it in the real world, your action sequence. And then at each step you compare whether what you can observe in the real world actually is what your model predicts should have happened. And if you find a discrepancy, then you have found a bug. And then shrinking works, it tries to, because maybe it's a very long, complicated sequence of steps, then it tries to simplify that by removing certain steps, and maybe you still have a bug until it can't remove more, and that's basically how that works, roughly, the idea. And that's actually also what we use at IOG to test our node, for example. So, and also there's a very nice other video by him where he explains how he found some very subtle Erlang bug with some of their databases. So he could test like database access and found some very subtle like concurrency bug with deadlock or something, very subtle really. And so you can do all these things. The basic idea is that, but it can be extended to I/O stuff, to side effects as well. Yes?
A simple one. Would it be possible to test maybe a different kind of environment? Maybe if you had a JavaScript environment, could you write tests in Haskell and then run that?
In principle, yes. You need some sort of test driver that can trigger, JavaScript stuff. But in principle, yes, you could. But probably there is something for JavaScript, because everybody stole from Haskell in that regard. So probably there is something in JavaScript already. But yeah, in principle, sure. It's the same as with read file and write file. You would just need some sort of mapping. You have some abstract. You would define some data type that represents these actions you want to do, whatever you want to do in JavaScript, and then you would need some interpreter function that takes those actions and maps them in I/O, and then the I/O action would actually execute that JavaScript. Start node with whatever. In principle, yes, you can do that as well. Nice point. So that's a fast. We could have like a whole course just about test, quick check, because there are lots of stuff. Also for blockchain, for example, things are often not deterministic, right? Because it's random which node does what, and so it's not so easy to write properties down because they are just probabilistically true. There was actually one very nice example. I explained in the first lecture about consensus, how that works in proof of stake, and I said this idea, even though it's not implemented in that way, is that you draw random Loveless, and then basically your chance of having the right to create the next node should be proportional to your stake, right? The more money you have, the more often you should be allowed to create the next node. And that is actually something that in the very first version of Cardano, the team, that's not us, so that was like, Karina likes them, she wears their t-shirts, but no, I'm just joking. Anyway, there was a team of young developers that were very inexperienced that wrote the very first version, and they did test that, but they didn't know quick check very well, so they basically just tested that if you have 1 million ADA, then your chances are higher than if you only have 1 ADA or something. They did it very roughly. And then John Hughes basically came in, he was hired, I think, to test their code, and he basically did it properly. So he really came up with a way to test statistical properties. So it should really be if you have P% of the total stake, you should produce P% of all the blocks. And he actually wrote a test that tests really that. So not just if you're rich, more blocks than if you're poor, but precisely. And he indeed found a bug. So he found with quick check that it was incorrect, and there was some subtle error that there was some wrong implementation, so it was a bit wrong. Nobody lost money because of that, because in those days, it was before Shelley, so there was no staking anyway. But there was an error in that part of the implementation, and he found it with quick check, even though it was such a complicated statistic property. So nothing that just says yes or no, it just says in so and so many percentage of cases this should be the case. But even that you can test with quick check if you are clever. Yes, so it's very powerful. And I mean, they did find real bugs, both in Cardano as also like in Erlang with Ericsson and phone switch networks. And
properties be like higher order? Can properties be higher order?
I mean, like this preserves, for okay.
Yeah.
I mean, maybe the question is whether you can randomly generate functions, and the answer is, I mean, for example, filter. Could you test something like filter with quick check? Mm-hmm. And I mean, the filter function on map on lists, and indeed you can actually. Maybe that's a fun. Let's say we make a mistake, or what? How could I make a good mistake?
Maybe math concatenating
Yeah.
twice.
Yes. Okay. Let's say. Okay, let's keep it simple. So I have a function from, let's say, int to int, and the list of ints. Sorry, my map. Sorry, I can do that properly. I mean, how can I do a good mistake? Let's say I do something like this. So I mean, but I wanted to implement a real map, and I made this mistake that I somehow did this. And now, of course, we wouldn't. Now we can have a property map preserves length. Maybe we could even use the original one. Yes. So let me reload. So we had this preserves length, so we can do quick check map. I mean, the real map preserves length. Maybe what's the real one? What's the two? Are this equal? Sorry. No, because the function. So let's say so I would need to, sorry, I would need to do okay, right, but it does work. I just don't know how to do it actually. There's a way. Sorry. So the question basically is, can quick check do functions? I mean, random functions. And it can. And I thought it's with. Yeah. So there are two ways actually. I mean, the classical one is this co-arbitrary class, but it seems that's not showable. But there's also this new one. Okay, and you do it with fun. Okay. So okay, the way is fun int. Like this, I think. Right. So there's a way, and now so for map it's true, and my map false. and it gives a counterexample for the function, and that I suppose means it's the function that maps every int to 0. And the list that just contains the 0. So yes, you can test higher order functions as well. So the QuickCheck can even generate random functions. And I don't know exactly, I've never used that actually, but there are somehow two ways. So there are there's another type class you need to implement if you want to generate functions, but it's possible. And then you can even do stuff like that. And you could test things like filter or map or sort. No, not sort, of course. Anything, really. Yeah, so QuickCheck is really cool. Yes. And of course, we have only scratched the surface. One other thing that's not mentioned, maybe I should mention this, with this property type, I always said it's Booleans on steroid. I mean, there are also nice things like, what did we have this drop twice? That was wrong. So for example, in the QuickCheck library, there's also, instead of this equals equals, there is an, let me just do this again. QuickCheck dropped twice. So we just get this error message. I mean, it's already good. It's falsified, and we get the values. But for example, there's also a QuickCheck operator equals equals equals. And then the only difference is this is no longer a bool, this is now a property. But equals 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 behaves exactly the same as equals equals. But now you get nicer error message. Now basically it calculates the left-hand side and the right-hand side and shows them. So it says, okay, that's not true what you say. For m equals 1, n equals -1, and x's equals list just 0. And in that case, if you say this should be equal, but indeed for these values, the left-hand side is the list, the empty list, and whereas the right-hand side is the list containing 0, and they are not empty. So and there is lots of stuff in this property thing. So I mean, so you can like give nice error messages, so it's easier to see what's going on. Yeah, that's one thing. But you can also just read the QuickCheck documentation on Hackage. I mean, there are also nice examples and so on.
And it's not a nice documentation.
Yes, that's one of the ones. I mean, I said at some point that QuickCheck is, Haskell is infamous for having bad documentation, but QuickCheck is certainly none of those. I mean, there's good documentation. So they have lots of examples in the documentation. Right. Any other questions?
Good question.
Very good question, yes. Okay, then we should probably stop for today. Thank you very much, and see you tomorrow.